Alrighty, in this week's pre-lecture video, we are briefly going to cover Kepler's 3 laws, and then we'll talk about Newton's law of gravitation. So Kepler's first law states that the planets orbit the sun in elliptical orbits with the sun at one of the focus points. So here are the two focal points of an ellipse, and here's a shape of an ellipse. And what Kepler's first law says is all planets have a elliptical orbit with the sun at one of these focus points. Kepler's second law states that planets sweep out equal areas in equal times. So let's say we're taking a look at the orbit of planet Earth. By the way, this orbit here is shown as an ellipse. What you'll learn in a few minutes is most of the planets in our solar system have a fairly circular orbit around the sun, which is a type of an ellipse. But anyway, we have exaggerated how elliptic the orbit is here. The point for Kepler's second law is that as a month goes by with the sun at this focus, the amount of area that this arc here carves out is equal to the amount of area that this arc here carves out. So in a month, if the planet moves this far on the orbit and sweeps out this area, these two areas are equivalent. And then Kepler's third law says that the period of the orbit squared is proportional to the cube of the semi-major axis. So here we need to introduce you to some terminology. A is the semi-major axis of a ellipse, so here's an example of an ellipse, and this is the semi-major axis. B here would be the semi-minor axis, and then this squiggly symbol just means that's not an alpha, by the way. It looks very much like an alpha, but it means proportional. And when something's proportional to something else, that's just like saying that t squared is equal to some constant of proportionality times its root. And t here, so t is the period of the orbit, meaning how long does it take for the planet to go through one full orbit. Now let's talk about this idea of eccentricity of an ellipse. Eccentricity of an ellipse is the measure of how elliptic that ellipse is. So this shape here is nearly a circle, but even a perfect circle is considered to be an ellipse with zero eccentricity, which is this quantity E. So let's take a look at what E is saying. E is saying that this distance from this center to one of the focus points divided by the semi-major axis is known as the eccentricity. For something like this ellipse here, well, C would be from here to here, and A would be from here to the end, which is a pretty large quantity. So this C divided by this A is a pretty high eccentricity. That's because this orbit here is pretty elliptic. Something like this that looks nearly circular has a lower eccentricity, or an eccentricity that is much smaller than 1, because the C value is much smaller than A. And you can look at the eccentricities of the planets in our solar system, and you can see that most of these values are pretty close to 0. Mercury is the most elliptic orbit. So in the case of orbits that are nearly circular, this A can be considered like a radius, because when a ellipse starts approaching a circle, this semi-major axis starts looking very much like the radius of the circle. So Kepler's third law for circular orbits just becomes that the period of the orbit squared is some constant times the radius cubed, because the semi-major axis radius of a circle if you treat a circle like an ellipse. Now, what does this constant of proportionality depend on? It depends on the mass of the central body only, and it does not depend on the mass of the orbiting body. So when we're talking about planets in our solar system, this constant ends up depending on the sun. It does not depend on the mass of what planet we're talking about. So let's try this example. Go ahead and pause the video and try this problem out. Okay, so once you've unpaused the video, gone through the example, let's go through the explanation. So which satellite has a longer period around the Earth? Assume that the orbits are circular and both satellites have the same mass. So we know that t, the period, is proportional to r cubed. So I write a version of this for satellite A and satellite B. Then I go ahead and solve for TA and TB. Well, this constant in front is the same for both. And then RA cubed square root divide, and then RB cubed square root. Well, we see that RA is bigger than RB. Well, if RA is bigger, then its cube square rooted will also be bigger. So we see that TA is greater than TB. All right, here's another example. Which satellite orbits with a longer period around the Earth? Assume that the orbits are still circular, but now satellite A has 10 times the mass of satellite B. Again, pause the video, think about this. Okay, once you've paused the video and thought about it, hopefully you started questioning, well, t squared is equal to some constant times radius cubed. We need to remind ourselves, okay, well, I see no mass of anything in here, so what is this constant dependent on? As mentioned a couple slides ago, this constant only depends on the mass of the central body and not the orbiting body. So it doesn't matter that A is 10 times heavier, this relationship still holds because the fact that it's 10 times heavier doesn't change anything in this relationship. Okay. The last thing in this pre-lecture video we're going to talk about is Newton's law of gravitation. So, Newton's law of gravitation says that the force, the magnitude of force between any two objects of mass m1 and mass m2 is given by this quantity, the gravitational constant, mass 1 times mass 2, or r squared. Now, what is this r? R is the center point to center point distance between the two objects. Note, it's not a radius. It's not the radius of mass 1. It's not the radius of mass 2. It is the distance from the center of this body to the center of this body. So the force with which green planet, or green mass, is pulling on blue mass, that magnitude is equal to the magnitude with which blue mass is pulling on green mass. And this comes from Newton's third law, which we have talked about in great detail in our previous chapters. So in the same way here, so before we've talked about one thing pushing on another and how much does the other thing push back. Well, if you have two masses, let's say two people standing some distance away from each other, and let's say one person is taller and larger than the other person. According to Newton's law of gravitation, the force with which person 1 pulls on person 2 is the same in magnitude with the force with which person 2 pulls on person A due to their masses. Now, the gravitational force between people, we'll do this calculation in class, we'll see is tiny. When you walk by people, you don't get pulled in by their gravity field because the force ends up being pretty tiny in terms of forces that we experience in our day-to-day lives. But in any case, the point is how much one mass pulled on the other is equal and opposite to how much the other mass pulled on the first. The last thing I want you to think through during this pre-lecture video before you come to class on Thursday is, well, we've been telling you F equals mg this whole time. So we've constructed the picture. Here's planet Earth. Here you are. Well, you're not going to look this large, but anyway, This is not to scale. Here you are standing on planet Earth or some distance away. Let's say you're up here on top of a mountain or something. We said that you always feel a force of gravity that's equal to mg downward. So how is it that this that we've been using can possibly be true when I just told you that the force of gravity between two masses should equal this expression here? So I want you to compare these two expressions and figure out why it's been okay that we've been using this. Or maybe, well, I haven't been lying to you. So this is not wrong. This is, in fact, correct and fine to use near the surface of the Earth. But I want you to figure out what's the connection between these two. All right, that's it for this pre-lecture video.